Can you believe it? Right now, Earth is moving at 600 kilometers per second, carrying you along for the ride. First of all, Earth itself is traveling at 30 kilometers per second, racing around the Sun. And the Sun, bringing its whole family along, is moving at 220 kilometers per second, weaving through the Milky Way. Meanwhile, the Milky Way itself is flying through the Laniakea supercluster. But this isn't the final stop. An incredibly immense force is dragging the entire Laniakea supercluster, moving it along. Our final destination is the legendary Great Attractor, known in English as the Great Attractor. To give you a more intuitive sense, we first need to zoom out and see what the structure of the universe is like. If you look up at the starry sky, you'll see countless stars. The Milky Way is a massive, ancient, and strictly organized collection of stars, containing hundreds of billions of them. Galaxies like this are common in the universe. Many are even larger than our Milky Way, with a higher density of stars. When so many stars gather together, gravity binds them into a coherent whole, exerting a powerful gravitational influence. The mass of these galaxies is staggering, allowing them to reach across millions of light years to attract one another. Sometimes they get too close and trigger a spectacular collision, merging into a new, larger galaxy. However, there's a cosmic tug of war. The space between galaxies is far vaster than the galaxies themselves. And in these empty regions, another force is at work: the expansion of space itself. The universe is expanding. This force tries to push galaxies further apart, at speeds that can even exceed the gravity pulling them in. This causes matter in the universe to become increasingly sparse. This is the famous Hubble flow. So, on a large scale, most galaxies follow the growth of the universe, moving away from each other uniformly. Most galaxies are destined to be lonely, never able to reach their neighbors. Only in very small, local pockets of space, like our local group, is matter density high enough for gravity to defeat expansion and collapse into a structure. While not all galaxies will collide, dense galaxy clusters will still influence one another. Their combined gravitational potential attracts even more distant galaxies, making dense areas denser and empty areas emptier. This is a self-sustaining process. Ultimately, this mechanism shapes the grand, universe-spanning skeleton, the cosmic web. It's like a giant sponge. Some regions are dense with matter, extending branches in all directions, while between these branches lie massive, empty voids. The cosmic web consists of giant galactic filaments, wall-like structures containing tens of thousands of galaxies, spanning billions of light years. Galaxies migrate within these filaments, converging like cosmic rivers, branching off, and the distances these rivers flow are hard for our brains to conceptualize. Within these filaments, smaller nodes are called galaxy clusters or superclusters. They contain dozens, hundreds, or even thousands of galaxies, acting as busy hubs in the cosmic transport network. Actually, the boundaries between clusters, superclusters, and filaments aren't that distinct. This is mainly because back when astronomers coined these terms, they never imagined that structures as massive as filaments even existed. We knew galaxies clustered together, but we never dared to think they could interact across billions of light years. It turns out we thought too small. Over the past 40 years, humanity has finally built a detailed, three-dimensional, galaxy-level space map. For humans living in a remote corner of the Milky Way, and who have only existed for a blink of an eye in this universe, this achievement is quite impressive. Through this map, we not only know where we are, but also who our neighbors are. Our local group includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and over 100 dwarf galaxies. But looking at it on the big map, we're actually just living in the countryside. We're located on the outskirts of a larger cluster, the Virgo Cluster. The Virgo Cluster has over 1,300 galaxies and is the gravitational core of this region. But it doesn't end there. The Virgo Cluster itself is just a small part of an even larger structure called the Virgo Supercluster, containing over 100 galaxy groups like ours. In the observable universe, there are an estimated 10 million such superclusters. The Virgo Supercluster spans over 110 million light-years, with a mass 7,000 times that of our local group. Sounds impossibly huge, doesn't it? Yet, even this isn't the final scale. In 2014, scientists at the University of Hawaii published groundbreaking research. They discovered the Virgo Supercluster is just a small component of an even more massive, intricate network. This truly grand structure is our home, the Laniakea Supercluster. Laniakea means immense heaven in Hawaiian. The name is quite fitting, as it spans 500 million light-years and contains over 100,000 galaxies. It is so colossal that for a long time, we didn't even realize its various parts were connected. Laniakea is made up of 4 major superclusters: our Virgo Supercluster, the Hydra-Centaurus Supercluster, the Pavo-Inda Supercluster, and the Southern Supercluster. Despite being separated by desolate cosmic distances, they are intricately linked together, creating countless galactic flows through space. However, the Laniakea Supercluster is so enormous that its overall density is actually not enough to keep it gravitationally bound forever. In theory, as the universe expands, it should slowly drift apart, disintegrating within the massive torrent known as the Hubble flow. But what we've actually observed has come as a huge surprise. While cosmic expansion is stretching this structure, we've found that everything within this entire supercluster seems to be drawn toward a specific spot in this region. The question is, what exactly possesses such terrifying power to hold a galactic megastructure of this scale together? Within galactic walls, the flow of galaxies is not uncommon. But the phenomenon here is much more than just a flow. There exists a gravitational anomaly with immense energy. It's like a giant anchor hooking the entire supercluster, or like a drain located at the bottom of a 500 million light-year basin. All galaxies are sliding toward it. This gravitational anomaly is what we call the Great Attractor. The Great Attractor, doesn't that name sound like a super black hole? It is the gravitational focal point of the Laniakea Supercluster. It's estimated to be located about 250 million light-years from the Milky Way. It's hungrily devouring everything around it. All matter within hundreds of millions of light-years is flowing toward this region. This usually points to 2 possibilities: either an unimaginable concentration of mass, like a superdense or massive galaxy cluster, or something even stranger, like a monstrous galactic black hole, or some kind of mysterious dark force countering cosmic expansion. In reality, the most plausible explanation is that it's an extremely dense supercluster of galaxies, with a mass so great that it influences the entire Virgo Supercluster and all surrounding galaxy clusters. But whatever it is, we face a most awkward and fundamental problem: we can't see it. This is the mystery of the Great Attractor. The most frustrating part is that besides its nature being a mystery, its location seems to be a prank of cosmic proportions. From Earth's perspective, the Great Attractor lies right behind the Milky Way's disk. As you know, we live inside the disk of the Milky Way. The galactic center has a bright core, along with thick layers of dust, clouds, and gas. These act like a heavy curtain, blocking out the light from behind the galaxy. It obscures about 1/5 of our view. This obscured region is known in astronomy as the Zone of Avoidance. Zone of Avoidance. Within this zone, the features of the Milky Way make it nearly impossible to detect anything behind it. Actually, there's nothing special about the space behind the zone. It's simply that our position is unfortunate, and our line of sight is blocked. It's like trying to see a distant landscape, but there's a massive pillar right in front of you. If humanity survives for another 100 million years, as the sun orbits the galactic center, we move to the other side of the galaxy. At that time, secrets behind the avoidance zone will be revealed. So, our current situation is: the local universe's largest gravity spot, the one dragging us along with everything else nearby, the main culprit, is hidden right in this blind spot. This has puzzled astronomers for a full 40 years. So how did we find it? The first sign of the Great Attractor appeared in the 1970s. Back then, we realized the Milky Way is moving through space. Technology was limited then, unable to see through the avoidance zone. About 40 degrees of the sky was unknown. But when mapping the first detailed cosmic microwave background map, clues appeared. The CMB is the residual heat from the Big Bang, filling the entire universe. Scientists found a dipole phenomenon. One side of the sky is slightly warmer than the other. It's not that the universe is uneven, but rather the Doppler effect. As the Milky Way moves at high speed, the radiation waves ahead are compressed, making it look warmer. Waves behind us are stretched, making it look colder. As we said before, galaxy movement is common. But the issue is speed and direction. If only considering cosmic expansion, all galaxies should generally be moving apart. But if something disrupts this, like gravity, galaxies gain extra motion. This deviation from expected expansion speed is called peculiar velocity. In simple terms, this is abnormal movement speed. When measuring the Sun's peculiar velocity relative to the CMB, we found we are rushing at 600 kilometers per second toward the direction of Centaurus. This is no accident. Something must be pulling us. But wherever we are headed, the destination is behind the avoidance zone. The cause of this peculiar velocity sparked years of fierce debate. The initial guess was simple: perhaps in that direction, there are just more unseen galaxies. Or else, since we're on the edge of the Virgo cluster, we are being pulled toward it. But calculations soon debunked these ideas. The Virgo cluster is huge, but its gravity can't explain our mad dash of 600 kilometers per second. There must be something even bigger. By the 1980s, with redshift survey technology mapping the universe in 3D, the mystery deepened. It wasn't just us moving. All galaxies near the avoidance zone were converging toward one point. In 1986, scientists estimated the source is 150 to 220 million light-years away. 2 years later, a team led by Donald Lynden Bell studied 400 elliptical galaxies. The best explanation was they were all rushing toward a great attractor behind the zone. Thus, the Great Attractor was born. To explain this flow in the local universe, scientists predicted the Great Attractor's mass is 10 quadrillion times the Sun. That's thousands of large galaxies. Astronomers were desperate to uncover the truth in the dark. Though visible light was blocked, times have changed. Technology advanced. We're not limited to the naked eye. Galactic dust blocks visible light, but from outside the galaxy, radio waves from superclusters and infrared can penetrate the dust. This gave us a small chance to peek behind the avoidance zone. The most effective tool is X-rays. X-rays are electromagnetic radiation. They penetrate the galactic plane, and X-ray sources in space are fewer than infrared or radio. This makes X-ray superclusters much easier to identify. They're like beacons in a dark sea. In 1996, René Croncourt-Toueg led a research team using Rosette satellite data. Deep in the avoidance zone, they found a previously undetected galaxy supercluster. This is the heart of the Great Attractor. Though in visible light, it's only as bright as the sky. Under X-rays, a massive galaxy cluster emerged. It is a Bell 3627, also called the Norma cluster. The Norma cluster is 220 light-years away, right near the attractor's predicted core. Its mass is 1,000 trillion suns. Without a doubt, this is a major part of the source. But even then, the team knew it wasn't perfect. The Norma cluster is huge, but not enough to explain our full peculiar velocity. The mass doesn't match. There must be something else. This led to wilder theories. Some scientists suggested since known structures can't explain this massive flow, maybe it's not gravity pulling us, but an unknown force pushing us, or a grander dark flow. This involves a concept called the dipole repeller. Just as in Laniakea, where galaxies flow to the Great Attractor, we found they also seem to be fleeing a region on the opposite side. That region seems to push galaxies away. Is there really anti-gravity or a dark power kicking us toward the attractor? It's not that mysterious. It's likely just a byproduct of cluster formation. Imagine this: when matter gathers into clusters, they pull from the surrounding space. Clusters get denser, while the space around them empties, forming voids. So it looks like the dipole repeller is pushing. Forget the name, there's actually nothing there, just a giant void. With no gravity to hold us, and the Great Attractor's strong pull, by comparison, we seem to be pushed away. It's more of a visual illusion. Since there's no mysterious force, back to the original question, if the Norma cluster is too light, what is pulling us to make us move so fast? In the early 2000s, the CIZA project was launched. It stands for Clusters in the Zone of Avoidance. Their goal was to completely sweep this cosmic blind spot. Using advanced X-ray tech, they found in the zone over 200 unknown galaxy clusters. But measurements were still disappointing. The total mass of these clusters is only 1/10 of the prediction. The conclusion was shocking: the Great Attractor isn't as massive as we thought. Yes, it's Laniakea's focus, but that's not the whole story. The CIZA survey revealed a more startling truth. Far beyond the Great Attractor, about 650 million light-years away, lies a more terrifying mass. The Shapley Supercluster. The Shapley Supercluster is one of the largest known structures. Though found in 1930, it wasn't until the late 90s that we realized its power. In 2005, CIZA confirmed that near Shapley is a region bigger than the Great Attractor, a denser area called the Shapley concentration. It has over 8,000 galaxies, 10,000 times the Milky Way's mass, 4 times the mass of the Great Attractor region. Now we believe this behemoth is the true culprit behind the Milky Way's mad dash. Here is the truth: our whole supercluster flows to the attractor, but the Great Attractor itself is pulled by the Shapley Supercluster. It's a nesting doll structure. Our 600 km/s speed is a combined effect. About 44% of the speed is from the Great Attractor, and 56% is from the more distant, massive Shapley Supercluster. With this puzzle piece, astronomers at could redefine our boundaries and map the Laniakea Supercluster. But does the story end there? Not yet. Just 5 years ago, in 2016, the team that found the Norma cluster, Kronkortuag and colleagues, found something new in the zone. Further than the Shapley Supercluster, about 800 million light-years away, they found a new supercluster, the Vela Supercluster. This might be the final piece. By calculation, it adds at least 50 kilometers per second. With the Norma cluster, the attractor core, and Shapley, plus the assist from the Vela Supercluster. The mystery that has haunted humanity for 40 years, the mystery of racing at 600 kilometers per second, has finally found a perfect explanation. So, what will the ending be? Since we are rushing toward them, will we eventually be sucked into the Great Attractor? Will Laniakea continue to be explored? Will our Milky Way be destroyed? The answer is almost certainly no. Although we are being dragged by these massive structures, moving against the tide, you should know, dark energy driving cosmic expansion is accelerating. This is a race between gravity and dark energy. And unfortunately, or rather, fortunately, gravity will lose. We will never reach the Shapley Supercluster, nor will we even reach the Great Attractor. Before long, dark energy will expand the universe so violently, that the gravity of the Great Attractor and Shapley will no longer be able to hold onto us. Although we currently look as if we are charging towards Centaurus, in reality, our only certain future is a collision with the Andromeda Galaxy, merging into one giant elliptical galaxy. While everything outside the local group will drift far away from us, our ultimate destination is the lonely void. Whether it's the Great Attractor or all those magnificent superclusters, they will eventually be torn apart by cosmic expansion, scattered into lonely islands. But that won't happen for a long, long time. We are very fortunate to live in such a golden age, where we can not only exist, but also observe such magnificent cosmic structures like Laniakea, watching them flow like great rivers. through the vastness of space, without vanishing beyond the cosmic horizon. Gravity can transmit its influence to such distant places, which is a breathtaking beauty in itself. Although the Great Attractor was once a mystery, in this vast universe, the greatest mystery is gravity itself, and that which has always gazed at the stars. Human curiosity.